Dr. Mahmoud Mashfejian.
Thank you, Clay. So I would like to welcome you for attending this webinar. Before I start, I would like to ask my colleague, Kindra Kruger, to introduce herself. Could you, Kindra, go ahead, please? Kindra, can you hear me?
I was on mute. That does not work very well. Hi, everyone. Good morning. Thank you for joining us. And Mahmoud, thank you for providing this webinar. I'm really excited about it. It should be a great session. I'm Kendra McGregor. I'm the Discipline Manager for Oil and Gas Processing, and I'm happy to be here. And I will be helping Mahmoud answer any questions that you all may have in regards to his presentation. And so we'll have a good discussion at the end as well. So thank you, Mahmoud, and good morning, everyone. And with that said, I'll hand it back over to you, Mahmoud.
Okay, thank you so much, Kindra. It's great to have you on board with us. The topic of my presentation is Hydrate and Hydrate Inhibition, and we're going to look at what are my options in dealing with hydrates. A brief introduction of myself. I did all my graduate studies at Oklahoma State University in chemical engineering during the 1970s. In my previous life, I've been professor of chemical engineering, worked at several different universities. Currently, I'm a senior instructor and consultant with more than 40 years of experience in oil and gas industry as well as in academic institution. I work at several different universities, like started with Oklahoma State University in Stillwater, Oklahoma, where I studied. Then I went to Shiraz, Iran, and I was their full professor for a long time, for almost 20 years. And it's my pleasure now that today one of former students, she's joining our webinar as well. In fact, there are many of our former graduates are working in Houston in oil and gas industries. Published more than 100 papers, in addition to more than 100 tip of the month, which are published on Petroskill John M. Campbell Company websites. And these tip of the months are very popular, and some of our colleagues are contributing to those tip of the months. I'm an experienced trainer specializing in oil and gas processing, senior member of AICHE and member of GPA Research Committee, subgroup 2. I've been full-time with John M. Campbell since 2005, and in 2014, when Petroskill acquired Campbell, I joined full-time in Petroskill, full-time instructor with Petroskill since then. So here are the learning objectives for our today's seminar. First, we're going to explain how hydrates are formed and the potential problems they may cause. We also list the hydrate former components and their contribution in the gas mixture, and also list options to estimate hydrate formation temperature, different methodology, as well as listing the options available to prevent hydrate formation. And we're going to make a comparison between them, pros and cons of them, and we're going to be discussing those. Also, we're going to describe the difference in the injection rates between methanol and MEG solution. These are two equilibrium inhibitors that are commonly used, and also describe pros and cons of hydrate inhibitors and their mechanism. Emphasis is going to be on equilibrium inhibitors as well as low dosage hydrate inhibitors like kinetic hydrate inhibitor and anti-agglomerate. With that said, let's look at see what are the requirements to form hydrates. You can guess from these 3 photos there are 3 main requirements. The main ingredient is water. So hydrate typically formed when liquid water is present in the system. However, this is not a requirement. Then another requirement is that the gas must be water saturated to form hydrates. Next, we need some light hydrocarbon molecules like methane through NC4 and components like carbon dioxide, hydrogen sulfide, and nitrogen as well. And typically, the size of molecule should be small so they can enter the cage, form a hydrate, and we'll be looking at that shortly. And the last requirement is hydrate formation temperature. So the temperature should be below the hydrate formation temperature. And normally hydrate formation temperature is much higher, maybe much higher than the freezing point of water. And also HFT depends on the gas composition and pressure. And sometimes instead of gas composition, we use molecular weight. And we're going to look at some correlation for hydrate formation temperature as well. So let's see how hydrate forms. To form hydrates, first water molecules, as you see in this diagram. These are water molecules at the corner of the surface. And they're bonded through the hydrogen bonding together. They form a cage. And if the temperature is low enough, a small molecule like methane can get into the cage or lattice, and then we have a solid phase, which is a mixture of water as well as a light molecule gas like methane or CO2, H2S, and nitrogen, as you saw before. The key is that the nominal size of the molecule should be less than the nominal opening of the lattice. So normally we have three types of structure 1, 2, and 3. You see the lattice configuration for each of them, and also the size of the opening for each structure. So structure, and you can see in the table on the right that component like nitrogen, CO2, H2S, methane, ethane, they can form hydrate, they can form structure 1, whereas bigger molecule like propane and IC4, they form structure number 2. Now let's see the contribution of, before I leave this slide, I'd like to mention that in our oil and gas processing, typically we have structure 1 and 2. We're rarely facing with structure H. So from our point of view, we don't care what kind of a structure we have. The important is know when we will have hydrate formation and how to deal with it. That would be our key concern. So this slide or this picture is from tip of March 2016, tip of the month, which is still on the John M. Campbell website, showing the impact of or contribution of different components on hydrate formation of a natural gas mixture. So this curve, let's consider a sweet gas with a composition shown at the bottom of the chart. And if I plot the hydrate formation pressure versus temperature for this composition, I get this purple curve. So any point to the right of this purple curve, we have hydrate formation it's hydrate formation free zone, no hydrate formation on the right side of the hydrate formation curve. And any point to the left of this, we may have hydrate formation. And let's take a look at some of the components like nitrogen, CO2, and NC4 with composition shown on the right. If we add them to our original sweet gas, they pull the hydrate formation curve to the left. That means they shift to a cooler temperature, which is good from our operation point of view. But components like propane, IC4, and H2S, they are a bad actor. They pull or shift the hydrate curve to the right. That means hydrate formation can take place at higher temperature, which makes operational problem for us if we are not aware of that. The takeaway from this is if we have a certain composition of propane, for example, in our process gas stream, and after a while we bring in more well to this production with higher content of propane, the hydrate curve will shift to the right, and that causes issue if you are not aware of that. And that's true also for H2S as well as IC4. So the main contributor of hydrate formation in gas mixture are propane, IC4, as well as H2S. Here is a photo of the vapor phase hydrate, and on the right side you can see as the hydrate melts, gas molecule like methane will be released, and we can ignite it by a match, and while hydrate is melting, gas is burning, and water will be released. This is a hydrate plug from a pipeline from Petrobras in Brazil. After they constructed pipeline, they tested the pipeline with water, and they drained the water, but they didn't dry it well. So when they started production, hydrates start forming. They could hear the knocking in the pipeline. So they assume they have hydrate. So they run pig, and the big chunk of hydrate came out. The points about this, the feed gas had contained about 10 ppm H2S, but when they analyzed the composition of the hydrate, the mole fraction or the concentration of H2S in the plug was about 69 ppm. So the key learning point is that hydrate is selective and picks up more H2S, and the concentration of H2S increase in the hydrate plug. That we should be aware of for handling, because as you all know, H2S is very toxic and poisonous, and if the concentration high, can cause fatal damage. So where hydrate formation can cause blockage and deposition, these are the list of the common places that could happen, like pipeline flow lines. And if that or pipeline flow line get plugged up, sometimes recovery may take from weeks to melt the hydrate or resolve the issue, and sometimes may cause shutting the production, which is loss of the money. In addition, it can happen in the wellbores, heat exchangers, especially chillers and gas exchangers, where the temperature is below the hydrate formation temperature. Another place that could take place is in expansion devices such as Joule-Thomson expansion valve or turbo expander. Again, anytime we have the ingredient water, small molecules, and temperature below the hydrate formation temperature, they start depositing. In addition, we also may have hydrate formation in the internals, especially in mesh pads, and they got clogged up, they got teared apart and caused severe problem. Just imagine if you have a scrubber upstream of a compressor with mesh pad and gets clogged up, and because the pressure build up, the mesh pad tears apart and you're feeding into the compressor, which may cause severe damage to your compressor. Here is an example of where hydrate formation takes place. This is a mechanical refrigeration system with make injection to prevent hydrate formation for a rich wet gas, which comes in the process gas, wet rich gas coming to gas exchanger, going through the tube side of this gas exchanger. We cool it down, we cool it down to say from 54 degrees Fahrenheit to about 16 degrees Fahrenheit. And the hydrate formation temperature for this kind of gas is normally about 60 degrees Fahrenheit. So we go below the hydrate formation temperature. If you don't do any inhibition, the hydrate forms and the tube get clogged up and cause severe damage and probably shut in to take care of that. To avoid hydrate formation, so we inject MEG or monoethylene glycol, and when we inject, we have to cover all the tubes, and we should have enough injection rate so good mixing takes place, because the inhibitor should reach the surface of the inside surface of tubes, because that's where the coldest temperature is. The cooling is done by residue gas, which is coming out of this cold phase separator. The temperature is low, so the process gets cooled. The residue gas is on the shell side, and the process gas in the tube side. So enough injection rate to have good mixing to protect every tube in the gas-gas exchanger. The same thing is true when the giving the gas-gas exchanger entering the chiller with a lower temperature. The temperature goes down to 5 degrees Fahrenheit. Again, the process gas going inside the tube in the kettle type chiller. And again, we've got to have making sure we have enough injection rate as well as covering all the tube sheet in this chiller. So if again we're going because MEG is expensive, we're going to separate it in three-phase separator, going to a regeneration process, and vaporize the contaminated water, and then we get lean glycol solution. We're going to pump it back to a heat exchanger. While the temperature is hot, we cool it down, and then we have lean glycol we use again. We do that because it's expensive. But there is some operational problem here. The condensed water or the water in the system may have salt, and salt accumulation takes place in the regeneration where the temperature is hot, because we're vaporizing water and the salt in the produced water get deposited in the system, and also the salt in the system may degrade the MEG solution, and we need to do some reclamation, which we're going to discuss at the end of the webinar. Another application is a pipeline inhibition. Suppose you have a natural gas flow rate of 9.5 million with a relative density of 0.65. It cooled down to 40 degrees Fahrenheit in a subsea pipeline. Assuming pipeline pressure is about 900 psi, the gas enters the line saturated at 90 degrees Fahrenheit, free of water. We're going to see how much inhibitor must be added in gallons per day to prevent hydrate formation. We're going to look at two scenarios. One for 80% lean glycol solution, and another scenario if you use methanol 100% lean methanol by weight percent. We're going to include the loss of methanol in liquid hydrocarbon and vapor phase hydrocarbon. And also, in addition to gas flow that was mentioned on top here, we have also some 90 cubic meter per day of condensate coming along with the gas in the line. The condensate relative density is 0.59, and molecular weight of the condensate is 55. And we will make comparison and then make decision which one we should choose and why we're choosing that. To give you a better view of what's happening, We have production facilities, say it's offshore facility. We separate the gas and liquids. The gas going through after the inlet separator. We go to a scrubber, compressor, we cool it down before going to pipeline. And the separated the condensate, we pump it and we merge it with the gas in the same pipeline. We send it on by a subsea pipeline to the shore. Then we're going to see again how much inhibitor we need to prevent hydrate formation. So next, let's take a look at what are the options for traditional hydrate formation temperature for a natural gas stream. We can use hydrate formation temperature as a function of pressure and the relative density. This could be a simple chart that we're going to see shortly. Hydrate formation temperature is a function of the pressure and relative density of the gas. Or we could use empirical correlation based on experimental data. There are three different types. One like CATS method, which is like the dew-point calculation method based on the K value for vapor phase and hydrate phase. And normally we use it's a trial and error procedure, and normally we use them for pressure less than 1,000 psi. The next shortcut method is Tracheal camber method for pressure above 1,000 psi up to about 6,000 psi. It's not trial and error, it's simple, and it's based on the hydrate formation temperature of methane, and then we add, based on composition of different components, we add contribution to the methane hydrate formation temperature. And the last method, shortcut method, is macro camber method for pressure above 6,000 up to 10,000 psi. And the detail of these methods are given in Chapter 6 of Volume 1 of Camber Gas Conditioning and Processing book. The next process option is a rigorous method by using equation of state, which is based on the equality of fugacity of each component in the vapor phase with the fugacity of the same component in the hydrate phase. This is tedious calculation and requires computer programming to use this methodology. And the last method is the Bailey and Weischer method, which is normally used for sour gas system containing H2S. Again, this is a shortcut method, graphical method, and you can see this method in GPSA data book or Camber book, Volume 1, Chapter 6 as well. And by the way, the detail of this process are covered in our G4 gas processing course, which is famous all over the world. So here's the simple hydrate prediction correlation. I should say the simplest one. The vertical axis pressure, and notice the scale is logarithmic. On the left-hand side, we have SI unit, and the right-hand side is FPS unit in PSIA. And these are for different relative density of gas. The top one is methane with relative density of 0.55. The next one is relative density of 0.6, 0.7, and 0.8. So for our case study that I introduced at the beginning, the subsea pipeline, we knew the pressure was 6.2 megapascal or 900 psi, and the relative density of gas was 0.65. So let's see what the hydrate formation temperature is. So I identify the pressure on vertical axis. Relative density is between 0.6 and 0.7. So by eyeball, I go to the mid between 0.6 and 0.7 is somewhere here. Then I draw a vertical line, and I read the temperature on top, 62 Fahrenheit, or the lower horizontal axis of 16.5 degrees Celsius. This is the hydrate formation temperature. And notice in the pipeline, the gas cooled down to 40 degrees Celsius Fahrenheit or 4.4 degrees Celsius. So we may have a hydrate problem, hydrate formation problem. Therefore, we need to use inhibitor. That's why the problem statement mentioned determine the injection rate for using either methanol or glycol. So simple methodology, quick estimation of hydrate formation temperature, which is good for facility type calculation and troubleshooting like that. If you're in this more accurate result, things like that, probably you need to go to simulation software. But this shortcut method is very quick and relatively good. The answer is good for feasibility study and troubleshooting, things like that. So we're going to determine depression temperature. Depression temperature we define as hydrate formation temperature, which is determined to be 16.5 degrees Celsius minus 4.4 degrees Celsius, which is the coldest temperature in line. So the depression temperature is 12.1 degrees Celsius, or equivalent to 22 degrees Fahrenheit. So we have to inject enough inhibitor to depress or shift the hydrate curve to the left. And we're going to look at this in upcoming slides. So you are familiar with the phase envelope for a multi-component system. It's pressure versus function as a function of temperature. We have the bubble point curve. Up to the left of bubble point curve, we have liquid. The blue curve is the hydrocarbon dew point curve, and the green curve is the water dew point curve superimposed on this phase envelope. And to the right of the dew point curve is gas phase, and in the middle we have two phases, liquid hydrocarbon and vapor phase. In addition, I can superimpose the hydrate formation curve, which is FGH curve. Now let's see. Point E is my operation point for the gas coming out of the separator, and this the phase envelope. Let's assume this is for the gas leaving the separator. At point E is on my operation pressure. Before I'm going to pipeline, I'm going to compress the gas, and then to get to point 1. Then I'm going to enter the pipeline. As I enter the pipeline, gas cools down till I get point 2. What happened at point 2? Because I hit the water dew point curve, the first droplet of liquid water forms. Do I get any liquid hydrocarbon? Not really, because I'm to the right of hydrocarbon dew point curve. So between the blue dew point curve of hydrocarbon and green curve of water dew point, I have liquid water, but no liquid hydrocarbon. But if I cool further down till I get point 3, where I intersect the hydrocarbon dew point, the first drop of liquid hydrocarbon forms. Now I have gas phase, liquid water phase, and liquid hydrocarbon phase. But since I'm still to the right of hydrate formation curve, no hydrate formation curve. But as gas moves through the pipeline, cools down to point 3, now we form hydrates. That's the problem that starts. Deposition of hydrate and causing trouble. So to the right of the yellow curve from point F to point D, I have 4 phases, including vapor phase, liquid water, and liquid hydrocarbon, plus hydrate phase, so 4 phases. So let's see how to deal with this if you don't do anything about this. Of course, the temperature profile could be something like this. So there is going to be curvature, a subsea pipeline. Now, we covered the first learning objective. Now let's see what's the next. So this is the option available to prevent hydrate formation. So here's some option, and we're going to discuss each of them, and we're also going to see the pros and cons during this webinar. First one, dehydrating the gas. Normally we use TEG dehydration. Control, the second one, control and maintain the system temperature above the hydrate formation temperature. We try to stay to the right of hydrate formation curve, and normally we do that with line heater and insulation of the pipeline. Sorry. Next is control and maintain the system pressure below the hydrate formation pressure. This is not very common, but again, one way of preventing hydrate formation. Number 4, inhibition with chemical inhibitors. There are two types of them: thermodynamic equilibrium inhibitors, or short we may say equilibrium inhibitors. That's including methanol and MEG. These are the two common ones, and sometimes, but not very often, we may use diethylene glycol. And of course, there is another glycol, TEG. We use that for absorption, dehydration. We don't use this guy. We don't use this guy for hydrate inhibition. This is just used for dehydration. But MEG normally used for hydrate inhibition. Then the next category is low dosage hydrate inhibitors. There are two types of them: kinetic hydrate inhibitor, which inhibit the rate of the cage. It doesn't shift the hydrate curve. These two guys, methanol and glycol, shift the hydrate curve to the left, or make the hydrate formation cooler. But this guy delay the hydrate formation, delay the kinetic of forming hydrate cage. So the hydrate doesn't form. It's a time dependent. And the next category of low dosage hydrate inhibitor is anti-agglomerate, which we allow the hydrate formation to take place, but keep them in small pieces and away from each other, so the hydrate doesn't form. And the requirement is to have liquid hydrocarbon phase. So the key getting from here, remembering that equilibrium inhibitors shift the hydrate curves, but low dosage one, they delay the hydrate formation process. They don't shift the hydrate curve. So now let's describe the differences in injection rates between methanol and MEG solution and what is the takeaway from it. So let's define our process again. For my pressure that I'm deriving from the separator, if I hit the hydrate curve, I had a hydrate formation temperature which I already determined using the simple chart, which was 62 degrees Fahrenheit. And now I know my coldest temperature in the process, which is 4.4 degrees Celsius or 40 degrees Fahrenheit. Now to make sure I don't form hydrate, I have shift this hydrate curve to this point. So how do I do that? I can use either methanol or glycol, which is, MEG. So how much should I depress it? From here to here, which is the difference between a hydrate formation temperature minus the cold temperature. For safety margin, we may shift the hydrate curve a little further to the left. So we define depression temperature as HFT, hydrate formation temperature minus cold temperature. For this process, 22 degrees Fahrenheit. And this is the starting point to determine the weight % of inhibitor in the process, as well as the injection rate and other related estimation procedure. So now let's see how much inhibitor must be added in liters per day or US gallon per day. for the same case study of the subsea pipeline. As I mentioned, there are different methods. I give the calculation result to save some time. I'm just showing the result of calculation, which I done by GCAP, which is a Petrosky Cameron in-house simulation program. It's not actually simulation, it's just a calculator or facility type engineering need. The top table for FPS unit or field unit, the lower part is for SI unit. As you can see here, the weight percent of methanol is less than weight percent of glycol solution, but the mole percent would be the same. The mole percent is the same, but weight percent are different. For the amount of inhibitor that needed to go to liquid water phase, for methanol is 112 or 113 pound mass per day. For glycol is 320, is higher. This phase is where the inhibitor prevent hydrate formation. But unfortunately, due to high vapor pressure of methanol, some of the methanol will go to the vapor phase, which is a hydrocarbon phase. And the part that goes to the vapor phase does not do any help in terms of fighting or preventing hydrate formation. But glycol has low vapor pressure, so the loss to the vapor phase is negligible, so we didn't do any calculation on that. It's very small, which is negligible. Then, due to high solubility of methanol in liquid hydrocarbon phase, some of them end up into the liquid hydrocarbon phase, which is condensate, 88.1. Again, glycol solubility is very low in liquid hydrocarbon phase, so we can ignore it. So as you can see, the total injection rate in terms of pound mass per day is about 430 pound mass per day, or equivalent to 65 gallons per day. Compare that to the 324 meg thermal pound mass, or 35 gallons per day. So which one is the injection rate, total injection rate is higher? Definitely methanol. And methanol is one-time use, but with glycol, we can, as you saw in that figure, we can regenerate it and reuse it. And also, please note that glycol is much more expensive compared to methanol on volume basis. The price of glycol could be as high as much as 3 times the cost of methanol. So methanol much cheaper. So what's the consequence of having a methanol in the vapor phase? Where this methanol goes in the vapor phase? This may end up with LNG plant, may end up with petrochemical plant and things like that. This can cause freezing in LNG plant, because freezing point of methanol is about minus 100 degrees Celsius or minus 148 degrees Fahrenheit. So it causes problem. And for petrochemical plant or oil refineries, this methanol in the gas is a poison for the catalyst. And in addition, the gas may end up in a emulsive dehydration. And again, methanol is a poison or degrade the emulsive 4A and loses its effectiveness, causing operational problems. So clients hate to have methanol in the vapor phase. By the way, if I convert this to ppm of methanol in the gas phase, it's about 300 ppm. So generally, the methanol loss concentration in the vapor phase in the range of 300 to about 500 ppm, which seems a small amount, but enough to cause operational problem for downstream equipment or downstream client. The problem issue with glycol, as we discussed, is salt accumulation and degradation of mix, so we have to do something about it. To save some time, I'm going to skip the same discussion on the SI unit, with the same kind of result in different units. So now let's discuss the pros and cons of hydrate inhibitors and their mechanism. Again, the focus is going to be on equilibrium inhibitor and low dosage. So the first prevention method was dehydration. Normally for field dehydration, we use TEG because TEG is much cheaper and commonly used in field and meet our requirement. Removes water from system, which is eliminate the source of the problem, which is water, and also reduce corrosion or no corrosion. Disadvantage, expensive, both CapEx and OpEx, and often not practical on offshore platform, and can be used for subsea application. On the other hand, in maintaining system temperature above HFT, most common is to use the line heater or insulation on gathering system or pipeline. Advantage, simple and robust, no chemical required, but negative aspect, expensive to heat, gas, or insulate pipeline. It may pose corrosion. Generally, higher temperature, more chance of corrosion. Another issue is reliability and also no production during shutdown. No protection during shutdown. So we have to have backup system. Let's compare methanol with MEG. Advantage of methanol, relatively cheap compared to glycol. MEG, low freezing point, can use as a mitigation in a cryo plant. We may use spray methanol at the inlet of the turbo expander to prevent hydrate formation, and normally transported in the vapor phase after injection point. And dissociation take place in downstream piping system. Disadvantage, high loss in hydrocarbon vapor and liquid, as you saw in that case study result that I showed. The rule of thumb, generally the loss of methanol to the vapor phase is 2 times the rate needed for the methanol to go to the liquid water phase. So huge amount of loss to the vapor phase. It's toxic, which damages the fishery industry or kills the fish. It's flammable, cannot be regenerated. Well, we can regenerate it, but it's very expensive, so rarely regenerated. As I mentioned, it's poison for petrochemical plant and degrades type 4A mold sieve, dehydration process, and pipeline limiting allowable oxygenate. And many pipeline operators, they have limit in terms of concentration of methanol or oxygenated molecules in the feed gas to their pipeline. On the other hand, making advantage stay where you want it to be, which is a liquid water phase or aqueous phase. The losses to the other 2 phases, vapor hydrocarbon and liquid hydrocarbon phase, is negligible, easily regenerated, it's less toxic and less environmental issue, and can inhibit down to -40 degrees Celsius or Fahrenheit. Disadvantage is expensive, as mentioned, roughly 3 times the chemical cost and the volume basis compared to methanol. and normally transported in the liquid water phase, less effective in dissociating plugs. One advantage of methanol, if you have plug in a pipeline, we may inject methanol from both sides of the plug to melt the hydrate. Glycol does not have this effectiveness for surface pipeline, but for the well, which is vertical, some people use MEG to melt the hydrate plug in the vertical, the tubing of the well, things like that. Another problem with the MEG contaminating water phase of produced fluid contaminate MEG, and that's why we need reclamation and taking care of the salt deposition in our regeneration system. More regeneration, more complex regeneration may be required to reclaim the MEG and prevent salt formation, things like that. So question is, which one should we use, MEG or methanol? You saw the result of interval injection rate. That overall glycol injection rate was lower, but there are other features as well. So let's take a look at the pros and cons. So the choice, it depends. Normally we prefer MEG for gathering system inhibition, but need to own both ends of the pipeline to do so. Next, MEG can easily be regenerated, but will only inhibit down to -40 degrees C and -40 degrees Fahrenheit. And normally, we cannot use that for lower temperature. If you have lower temperature, normally we use methanol. Gathering system chemicals may build up in the regeneration, requiring reclamation. However, for methanol is generally used in application that intermittent inhibition require, or where like intermittent would mean like startup or shutdown during periods of cold winter, like cold weather, like winter time. So we don't use it all around the year. Another option or choice, we may use methanol where MEG injection or TEG dehydration is not practical. Example of this would be cryo, where temperature is very cold. We may use methanol in the inlet of the turbo expander process, or we cannot do the TEG dehydration upstream of the cryo process, things like that. As I mentioned, can inhibit down to -100 degrees C or -48 degrees Fahrenheit, and that's why it's good for cryoplant plugs. And methanol contamination, both vapor and liquid hydrocarbon phases, is becoming a significant issue. Nowadays, more awareness and client demand much less methanol in the gas receiving. In addition to natural gas, there is some limit nowadays on amount of methanol in liquid LPG as well. And there are a couple of research projects going on in GPA committee. The Colorado School of Mines is the contractor working on finding ways to minimize methanol injection for LPG product, because this LPG causes a problem when it's end customer is using it, like damaging the internal combustion engine and environmental pollution and many other issues as well. So there are different technologies for reclamation of MEG, so we can reuse it. Chapter 6 of Campbell volume textbook, Gas Conditioning and Processing, describes the detail of this process. And if anybody interested, I suggest that reference. And also there are resources and some papers and that can be referenced to get more detail. And normally this kind of system is designed by vendors. Here's another configuration for reclamation of methanol. This is for a source extraction option. Another issue is salt formation in the system. It's important to the understanding of the chemistry of physics of carbonate and sulfate in combination with the different divalent such as calcium, iron, magnesium, barium, strontium, etc. They form severe salt formation or deposition when they get in contact with carbonate and sulfate, and severe deposition takes place. This is the deposition of this kind of salt, and this is after removal. You can clog up your piping system completely. By the way, this reference here is a paper OTC Offshore Technology Conference, paper 17-355. If you are dealing or having problem issue with salt, meg regeneration and salt formation in the system, it's an excellent paper. So let's talk about low dosage inhibitors as well. And as we mentioned, they do not change the equilibrium hydrate formation condition. In other words, they don't shift the hydrate curve to the left. They require much lower concentration. The required concentration normally less than 10,000 ppm, whereas the concentration of the methanol and glycol could be in the range of 200 to 400,000 ppm. On weight basis, they have lower inhibitor losses than equilibrium inhibitors, reduced capital cost of delivery, no regeneration is required. We mentioned there are two basic types, kinetic inhibitor or threshold inhibitor, KHI or THI, sometimes they call it, stand for threshold hydrate inhibitor. As we mentioned, they slow down the rate of hydrate formation because hydrate formation is a crystal formation, is a kinetic process, so it delays the hydrate formation and extend the period of time by increasing the induction time for hydrate formation, which is at crystal or lattice. Grow for anti-agglomerate inhibitors, the second type of low dosage inhibitor, allow hydrate formation, but prevent the agglomeration of sub-millimeter hydrate crystal. So the crystals are small, we keep them separated from each other so they don't deposit, they don't precipitate and won't cause operational problem. And to keep them dispersed or use this type of anti-agglomeration, definitely we need to have liquid hydrocarbon phase. So let's take a look at pros and cons. Advantage, non-toxic, no discharge, produced water, and discharge is produced water because they are not toxic. Can be used in conjunction with equilibrium inhibitors. If you use in conjunction, the equilibrium inhibitor usage goes down drastically. I did a tip of the month based on the information we have through a published paper for offshore subsea. line, the injection rate went down from 125 barrels per day to say 25 barrels per day when you combine kinetic inhibitor with the equilibrium inhibitor. Interference with other chemicals limited, for example, with corrosion inhibitor or other chemical we use in our system. Degree of subcooling limited to 28 degrees Fahrenheit in suite system. Disadvantage, degree of subcooling allowed depends on the system resistance time. The shorter resistance time, the better effective they are. If the resistance time of your gas in the line or the system is long, definitely you may have hydrate formation. Cannot be used for melting hydrates that already form. Something that methanol can do that. Hydrates, high salinity produced water may cause kinetic hydrate inhibitor to come out of the solution and high chemical cost, but this is cost per unit volume, but because you're using lower dosage, overall cost could be less than using equilibrium inhibitor, but they are less proven compared to the equilibrium inhibitor. Pros and cons of anti-agglomerate. The advantage can achieve subcooling greater than 40 degrees Fahrenheit. Remember, here was only 28 degrees Fahrenheit, so combination of these two may extend the subcooling period. Can perform for longer period of non-flowing condition. That's for shutdown condition. But still, for shutdown condition, normally the one that's used is methanol. Methanol is used for shutdown condition to prevent hydrate formation for no flowing condition. Disadvantage requires a hydrocarbon liquid phase. Otherwise, it won't be effective. Possible emulsion formation in hydrocarbon liquid phase. So that's the negative aspect. The presence enhanced emulsion, which makes separation of liquid hydrocarbon and water more difficult. Most inhibitor lives with crude or condensate, but residual concentration in produced water can exceed the toxicity limit for discharge on offshore platforms, things like that. Chemical compatibility with production fluids is another negative aspect of it. May require heater at production equipment to melt the suspended hydrates. And also track record less proven. In general, the most common one, most widely used are the equilibrium inhibitor. They are more reliable. Low dosage one are used as well, and overall cost may come lower if you use the kinetic hydrate inhibitors or combination with anti-agglomerate low dosage hydrate inhibitors. So let's take a look at the impact of hydrates on our production facilities, production and processing facilities. The impact is very significant on the design. It affects our concept selection. We have to decide, separate the phases, like have one pipeline for gas phase, one pipeline for liquid hydrocarbon phase, or have a full stream, single pipeline. That's a major decision because there are lots of things associated with this. These separate phases require, for example, for offshore require more equipment and more processing facility needed. So it's a major decision because of CapEx and OpEx. Installation requirement. Needs for chemical line, injection points, storage, pumping capacity, safety, and sometimes transportation of the from shore to the offshore facility as well. Operational procedure is very important, especially for during shutdown, startup, as well as during clogging takes place. But to have good solid procedure to avoid any accident or fatal damage. Also, flare capacity is of concern. In addition to flare capacity, we have to have pigging and big capability to remove the hydrate deposit from our pipeline. Otherwise, we're going to have higher pressure drop and reduction in flow rate as well. So in summary, for our webinar, we can say Hydrate and Inhibition have significant impact on the design and operation of production and processing facility. I hope you agree with me on the first one after watching this webinar. Utilizing a suitable prevention method eliminate the risk of hydrate formation and blockage of equipment, flow lines, and pipelines. So we saw several of them. So we got to use a suitable one which works best for our scenario. So accidents due to hydrate blockage have caused many injury and deaths, often when engineers and operators are trying to get the blockage melted without completing the appropriate hazard reviews. In the past, they injected methanol from one side of the pipeline. Once the side that starts melting, pressure build up, and the other side low pressure, and then high pressure started moving the hydrate plug, and then you had the rocket in the pipeline, and we tear apart the pipeline because of the movement of a heavy plug with the force of the high pressure from one side. From this accident, we learned a lot, and people modified their operation to melt the blockage. And then they injected methanol from both sides. Again, accident took place because there were two plugs in the pipeline. So you have to be aware of all these scenarios and have good operational procedure in place to avoid repeated accident. Number 4, the business impact of not understanding the hydrate prevention in our process facilities and pipeline can be significant. And I hope this high-level overview will give you a better understanding of hydrate and hydrate inhibition and what option we have for prevention and so on. Our G4 courses cover in detail to deal with hydrate formation and prevention as well. If you guys are interested, if you have not taken G4 yet, that's a good course to take. Good news, you're going to have a fun, which is a Kahoot quiz. Bad news quiz, but don't worry. It's also evaluating my performance as well. So we're going to use Kahoot quizzes. Please take out your cell phone out if you would like to join us to do the quiz together. In your browser, type kahoot.it, and the presentation show you a game pin number. Enter the or type the pin into your phone. Type your name when prompted. You may use a nickname if you wish. Watch presentation for quiz question, but select answer the question using your phone. Be quick because time is limited. The fastest you respond to the question, the more points you get. So not only you need to know the answer, you've got to be fast as well. With that said, let's do the quiz, then we do the question. There are about 10 quiz questions. So let me pop up the quiz and show you the pin number. Display. Display. Here's the pin number on my screen. I like the choice of your nickname, Hydrate, Quick Draw, Micro. Okay, I'm going to start. I hope you could join us. Last chance to log in. Let's get started. So we got both MEG and DEG or DEG, MEG and DEG. They're both correct. So A plus B is the correct answer. TEG, we use it for dehydration only. TEG for dehydration only. We got Victor, Mani, and Dexter. They are very close to each other. Majority got it right. So shift the hydrate HFT curve to the cooler temperature, which is to the left. Victor is on top now, followed by Gigi and Mani. Awesome. Perfect. The 3 requirements, all 3 are listed here. Good job, Victor, Gigi, and Mani, and Hydrate as well. So H2S, shift the hydrate curve to the warmer temperature, which is to the right. In addition to H2S, propane and IC4 do the same thing as well. But CO2, nitrogen, and normal butane shift the hydrate curve to the left. In a way, they inhibit hydrate formation of natural gas. Victor is still on top. Good job. Followed by Gigi, Mani, and Nushi. So 2 correct answers. 1, depending on the quantity of free water. The more water condenses in the system, the more inhibitors you need. And the higher depression temperature, the more inhibitors you need. The more inhibitors you need. The other 2 is not correct. Machine is getting close to the top. Good job. Victor and JJ are still leading. So gas A, because gas A had 20% H2S, that's a higher or warmer HFC. Victor is still on top. Good job, Victor. But you've been followed very closely by Gigi and Nushin as well. So all 4 correct. All 4 correct. Victor, you lost your leading, but it's still there is time. Very good. Majority got it right. So propane is hydrate inhibitor. Shift the hydrate curve of natural gas to the right, like IC4 and H2S. All right, congratulations, Nushin. But be careful, JJ and Victor are following closely. Perfect. Everybody got it right. Good job. Very good. Methanol has a high vapor pressure, low freezing point, and cheaper compared to glycol. This last chance. And majority got it right. The two answers slows the mechanism of hydrate formation, requires much lower dosage. But the other two, the low dosage, they don't shift the hydrate curve. They delay the hydrate formation time. And the capex is less compared to equilibrium inhibitor. Congratulations, Victor. Nushin, you lost the last one, but still congratulations. JJ, you're back. I knew you're going to get back. Good job, everybody. Okay, it's time to answer question. Kindra, do you have question?
Hi, Mahmoud. Yes,
You're
can
on
you hear
mute.
me? Can you hear me now?
Yep, all good, Kendra. Oh, hey, Kendra, you're muted again there. Maybe hit the button.
How about now?
Yep,
I
there we
can
go.
hear you.
All good.
Okay, we're good. You guys can hear me?
Yep.
All right. Okay, so we do have a number of questions. The first question that I would like to ask is there was a question as to what was driving the methanol going into all the other phases. So we saw quite a bit went in the vapor phase and almost twice as much as what you needed in the water to do the hydrate inhibition. But we also saw that a lot of the methanol went into the condensate phase. And so, Mahmoud, do you mind discussing what's driving the methanol distribution, and also why is it that the MEG only stays in the water phase?
Okay. To vapor phase, the driving is the very high vapor pressure of methanol. Its vapor pressure is much higher than vapor pressure of water, and vapor pressure of glycol make is very, very low. So that's why you don't get any make going to the vapor phase, but a lot of methanol going to the vapor phase. For the liquid hydrocarbon, again, the same thing. Solubility of methanol in liquid hydrocarbon is higher, but the solubility of glycol in liquid hydrocarbon is much lower, so we can neglect them.
Okay, excellent. The next question that we have is, why does the hydrate structure always have water in it? Is there a way to have a hydrate structure that does not include water as the lattices?
No way. So the criteria, you have to form the cage, the trap, so the gas molecule get trapped in the cage.
Okay.
The only time we could have solid formation is ice with no gas. So if you cool like water to low temperature of 0 degrees Celsius or 30 degrees Fahrenheit, you have solid phase, but that's not hydrate, that's ice.
Okay, excellent. Thank you. Okay, so the next question is, it was a bit of a comment, but I think we should discuss it because I think this is an important point to make. So there was a comment here saying that you cannot spray the MEG onto the tube sheet because it will run down and preferentially go through the bottom row of the tubes. And so the comment was made that you need to use CFD to determine the best place and spray pattern. And I guess, you know, ultimately that is the most ideal situation. But, you know, if I think about the number of plants that have been built prior to CFD, certainly back in the day, what we could do is figure out, you know, where the most effective place and nozzle selection to put those sprays in the both in the gas exchanger and the gas chiller through operational experience. So, I mean, certainly we'll know when we start getting hydrates in there, and so that, you know, isn't ideal. But then again, also from experience. And so, Mahmoud, do you have any thoughts or comments in regards to that comment?
One thing I forgot to mention, that in those mechanical refrigeration with make injection, the calculation I showed, it showed you the rate required for injecting MEG. If it was not for pipeline, it was for that process. Mm-hmm. We normally multiply that flow rate by a factor of 2 to 3, make sure we have a good mixing and covering all the tubes.
Yes, that's an absolute key point. So that's a good point to make. So certainly when we're going into a very deep depression temperatures like we would in a NGL extraction plant where we're using mechanical refrigeration, or, you know, maybe we're using a JT valve, in those instances, certainly we will be over-injecting by at least 3 times to ensure that we do get all of those tubes fully satisfied in terms of the injection rate.
But some people may ask, Mahmoud, that's going to be cost much higher. My answer is the injection rate is low, so when you multiply by 3, it's not going to make that much difference in terms of cost, but the cost be a little higher, not that 3 times.
Excellent. All right, so those are really good points. I have another question here, and the question is, basically, what type of inhibitor can be used for CO2 injection for storage?
CO2 injection, methanol normally enhance solubility of CO2 in water phase. That's the negative aspect of methanol. Depends on the application. Is it pipeline?
Well, so, you know, we don't have the full scope. I did reply to the individual who asked the question. But from my perspective, if we're doing, if we're going to do CO2 injection for storage, then really the best practice in that instance is to figure out the appropriate location to dehydrate that CO2 in the compression train, just to ensure that you will never get either hydrates or water dropping out downstream of the compression train going into the pipeline, which ultimately ends up in the reservoir. In terms of trying to inhibit inhibit any hydrates forming, once you're past the compression train, is that the only place for it to go is going to be the reservoir. And I would think that any type of hydrate inhibitor going into the reservoir could potentially cause some problems. So that's something that we can follow up with our CO2 guys to see, if they have any thoughts or comments around there. But for what it's worth, that would be my recommendation. Just remove the water so you don't need to worry about it.
Exactly. The best remedy is dehydration. And keep in mind, the water CO2 behavior is not like hydrocarbon. As pressure increases, the water content goes down. It's pressure about 1,000 psi, if I remember correctly. Then at higher pressure, the water content of CO2 increases. So you have to be aware when you do the dehydration of CO2.
Right, and so really that's an optimization in terms of looking at the compression train and figuring out, where does it make sense to put the TEG dehydration unit in terms of that compression to minimize that process size. Certainly.
Exactly.
Okay, there's another comment. So if I'm going to dehydrate offshore, and then in that instance, what type of glycol would you typically recommend, Mahmoud?
And normally TEG as well, with dehydration if you use this.
Excellent.
Because most of it is more expensive and much heavier compared to the TEG.
Yes, sir, absolutely. And the other thing, if we're going into a subsea pipeline, we don't need to be bone dry. So that's why oftentimes we will see, in place of doing any type of hydrate inhibition using, say, MEG or DEG or possibly methanol, that we will just simply dehydrate either offshore at the platform, or possibly, we're going to dehydrate out at the well site, or maybe at compressor stations if we're onshore at various locations. So anyways, I think that covers all of the questions. Clay, did I miss anything in the chat that you see?
No, I think we covered it all. Thank you, Kendra.
Okay, excellent. Well, thank you, Clay, and thank you, Mahmoud, for the great presentation.
And thank you to you, Clay, and all the participants for their patience and attending the seminar. They did really good on the quizzes as well. And I wish them all the best.
All right. Thanks, everybody. Have a great rest of your day or evening, and we hope to see you in future sessions. Everybody take care.
All right. Bye, everyone.
Bye all.
Bye.